Hello, good afternoon, everyone. My name is Akata, and we are going to start with the fourth talk session of oral talk session of the AGM GCPR 2020. We are going to have 5 talks in this session. 2 of them are long orals and 3 of them are short orals. After each talk, we are going to have time for discussion, and for those of you who would like to ask questions to the authors, please log in from Discord. You can find the link to Discord for this session next to the talks for text before the YouTube icon. We will start with Apratim Bhattacharyya. He's going to talk about high wavelet-based block autoregressive flows for trajectories. You can go ahead, Apratim.
Thank you. Let me share my screen first. Okay.
Yes.
Hello, everyone. Welcome to our talk on hard wavelet-based block autoregressive flows for trajectories. I am Apratim Bhattacharyya, and this is a joint work with Christoph, Straehle, Mario, Fritz, and Bernt, Schiele. In this work, we focus on the task of prediction of future trajectories of traffic participants, for example, pedestrians. Prediction of future trajectories over long time horizons is important for the success of autonomous agents, such as self-driving cars. Accurately modeling the multimodal distribution of likely future trajectories remains challenging. Issues such as missing modes are observed in prior work. In this work, we propose a novel normalizing flow-based exact inference model using Haar wavelets, HVA flows, to effectively capture the multimodality of pedestrian trajectory distributions. We begin with a short introduction to normalizing flows. Normalizing flows are a type of generative model which allow for the computation of exact likelihoods. In other words, they allow for exact inference. Normalizing flows consists of a series of bijective, that is invertible transformations, here shown as GI on the left, that transform a target distribution over y, the variable y, to a specific base or prior distribution over the variable z. We show a simple 2D example of a normalizing flow on the right. Normalizing flows allow for the computation of exact likelihoods using the change of variables formula. Therefore, transformations whose Jacobians are efficient to compute are preferred. Next, we contrast normalizing flows with generative models, which have been popularly used by prior work for trajectory prediction. Prior work on trajectory prediction has mostly focused on conditional variational autoencoders and conditional generative adversarial networks. Unlike normalizing flows, conditional variational autoencoders maximize only a lower bound on the data log likelihood, the tightness of which is hard to control in practice. Conditional generators do not explicitly maximize the data log likelihood. This makes it challenging to fully capture multimodal trajectory distributions, leading to issues like missing modes. The recent success of normalizing flows on complex data, such as images, have been driven to a large part by split coupling flows, a type of normalizing flow which allows for easier parallelizability of both sampling and inference steps. While most prior work on split coupling normalizing flows are focused on image data, only recently works such as flow wave nets have considered sequential data, that is, for example, audio or speech synthesis. However, split coupling normalizing flows fail to fully capture long-range spatiotemporal correlations, instead encoding only local correlations. This makes it challenging to fully capture the multimodal trajectory distribution with split coupling normalizing flow-based models such as flow wave nets. Therefore, in this work, we propose our hard block autoregressive flows or HBA flows to address the limitations of split coupling flow-based models. Now we discuss our HPA flow model in detail. Our HPA flow model consists of K coarse to fine scales. Given the initial observation X, that is probably the past history and other contextual information like images, the trajectory that we want to model, that is Y, Hard-wavelet-based transformations are applied at each scale to obtain downsample coarse and fine components. Normalizing flows are used to model the fine components. Normalizing flows at each scale are block autoregressively conditioned on the coarse trajectories. The coarse trajectories provide global context to the normalizing flows at each scale. This enables our HPA flows to better capture long-range spatiotemporal correlations. Next, we'll look at the hard transformations in more detail. Given an input trajectory Y, the hard transformation at the kth level consists of a downsampling or averaging operation, which leads to the coarse trajectory, that is CK, and a subtraction operation, which leads to the fine or detailed component FK. We can also see this as a bandpass filter. The proposed transformation is invertible, and the Jacobian, as we show in the main paper, is a function of the length and dimensionality of the trajectory Y and can be computed efficiently. As the proposed hard transformation is invertible, the log likelihood of the data can be computed using the change of variables formula. First, after the first hard transformation, the data log likelihood of our HPA flow model factorizes autoregressively into the likelihood of the fine component, that is F1, conditioned on the coarse component C1, and the likelihood of the coarse component C1 plus the Jacobian of the hard transformation. Again, note that the distribution of the fine component F1 is modeled conditioned on the coarse, that is the subsample component C1. This provides global context to help capture long-range spatiotemporal correlations. The coarse trajectory C1 is further recursively decomposed using the hard transformation. The log likelihood after K transformations can be obtained by the recursive application of the change of variables formula. Again, the distribution of the fine components, that is Fk, is modeled autoregressively conditioned on the coarse component Ck. This provides global context at each scale or level K. Next, we discuss how the conditional distributions, that is P of Fk, Ck, and X, are modeled. The conditional distributions, that is P of Fk given Ck and X, are modeled using conditional split coupling flows. In particular, we use shallow conditional split coupling flows based on flow wavenets. These support variable length trajectories and allow for parallelization of both desampling and inference steps. The log likelihood of each of the fine components, that is log of P of Fk given the conditions, can be expressed using the change of variables formula. This decomposes again into the likelihood over the base distribution, that is P of Zk given Ck and X, and the log determinant of the Jacobian. Finally, note that unlike prior work such as flow wavenets, our proposed factorization allows for the base distribution to be conditioned on the coarse trajectory Ck. In particular, we employ Gaussian distributions whose mean and variances are functions of the coarse trajectory, that is Ck, and the observed or the past trajectory X. This allows for improved modeling flexibility by encoding dependencies in the latent space. Next, we discuss the sampling step of our HPA flow model. As the model is invertible, sampling occurs by inverting each block in our HPA flow model. In detail, we sample the coarse scales first, followed by subsequent finer scales. Note that the number of levels K, this capital K, is upper bounded by the logarithm of the trajectory length. Thus, the number of sampling steps grows logarithmically in trajectory length, provided sufficient parallel resources. This this is significantly faster compared to fully autoregressive approaches. We now evaluate our HPA flow model on the Stanford drone and intersection drone data sets, which consists of trajectories of diverse traffic participants in complex traffic scenarios, such as—
Apratim, sorry to disturb. Your slides are not moving.
Oh.
They are frozen.
Okay, is it moving now?
No.
Okay, 1 second. I'll reshare the screen. Okay, was it moving now?
No.
Now?
No. We actually can't see the slides.
Okay.
You start again, yeah. Yes, now it's fine.
It's fine?
Yes, we can see the slides.
Okay, so we move to the, so we evaluate on 2 standard benchmark datasets, that is Stanford drone and intersection drone datasets. And as metrics, we focus mainly on metrics that that aim to match the true distribution to the predicted distribution. In particular, we look at the Euclidean error of the top 10% of trajectories. This has been shown by prior work to be quite robust, and also the negative conditional log likelihood, which again matches the ground truth to the distribution to the predicted distribution. We first evaluate on the Stanford drone data set, which shows that our HPA flow model can effectively capture the multimodal trajectory distribution. This is supported by both the accuracy, that is the top 10% accuracy, and the negative conditional log likelihood. In particular, we outperform both conditional VAE-based models such as BMS-CVAE and CFVAE-based models. Furthermore, we also outperform split coupling flow-based models such as flow wave nets and autoregressive models such as video flow. We further evaluate the sampling speed of our model. Here we compare against various state-of-the-art approaches, including flow wave nets and CFVAE and autoregressive models. We show in particular the time that it takes to sample one batch of 128 samples. We see that our HPA flow model leads to better accuracy along with competitive sampling speeds. Finally, we also evaluate on the intersection drone datasets, which again confirms the results that we saw on Stanford drone. That is, our method outperforms VAE-based models, split coupling flow-based models, and autoregressive models. Finally, to conclude, our HPA flow model improves modeling flexibility with a coarse-to-fine block autoregressive structure, where coarse trajectories provide global context and helps us capture long-range spatio-temporal dependencies. Our HPA flow model requires significantly fewer sampling steps compared to fully autoregressive approaches, which leads to competitive sampling speeds while not sacrificing on accuracy. Finally, we demonstrate state-of-the-art results on true real-world datasets, that is, Stanford drone and intersection drone. Thank you for your attention.
Thank you for the presentation, Apratim. It was very interesting. I have one quick question. Do I understand correctly that your model is able to trace multiple objects at the same time?
Yes.
Okay, and up to how many objects have you tried?
So I think the default, it depends upon the setting. There is absolutely no limit on the method. So, but generally, I think the maximum number of objects is, I think, limited to 32, but you can increase it. There is no theoretical limit. But of course, if there are more and more objects, then it becomes harder and harder to effectively capture the joint distribution of all these objects.
Okay, thank you. So for the audience, if you would like to ask questions to our speakers, please post them on Discord. And you can find the icon to Discord for this session next to the YouTube icon on the main web page. Now we can move to our next speaker. Yunlei Tang is going to present his work with the title Center-Based Monocular 3D Object Detection with Joint Depth Understanding. You can share your screen, Yunlei.
Yeah. Is that now visible?
Yes.
Okay. So, thank you, Zina. So, welcome everyone. My name is Yunlei Tang. Today, I will present our paper, Center-Based Monocular 3D Object Detection with Joint Depth Understanding. This also refers to my master thesis, which is done at Technical University Darmstadt and cooperated with Audi. Center-3D is a one-stage anchor-free approach to efficiently detect the 3D object using only monocular RGB images. Today, by explaining the different phrases of the title, we can take a deep look into this approach. So firstly, let's spend some time to introduce the concept of the monocular 3D object detection, which is also the problem our approach tries to solve. The input of the network are the monocular, or to see the single 2D RGB images of the autonomous driving scenes. After the inference of the network, we want to locate the object of interest like a vehicle, pedestrian, or cyclist on the 2D image plane, as well as in the 3D physical space. So to this end, we need to detect the object and estimate the several properties like 2D size to rebuild the 2D bounding box, the physical 3D dimension, and also the orientation according to the camera to recover the 3D cuboids. And also for visualization, we can project the detection either back to the 2D image plane or in bird's eye view. So basically, this is the output we expected to generate. The next phrase of center-based refers to our baseline network of our approach, object as a point. We can also call it a centernet. Centernet is also a one-stage anchor-free approach. It models an object on heat map as a single point, the center point of the 2D bounding box. We applied this basic motivation and structure in our work, so it worth to explain it a little. So each input RGB image will be fed into the network, passed through backbone network to generate a general feature map. Then the separate head layers with similar structure will be connected afterwards to estimate the different feature maps like the heat map for each category and other properties required for 3D detection like introduced before. And especially, the heat map describes a confidence score for each location with a Gaussian kernel. The peaks in this heat map thus represent the possible 2D center of the object. All other properties are then regressed and captured directly at the center locations on the feature maps, respectively. So from the view of the structure, based on the 2D center from a heat map, they can rebuild the 2D bounding box with the 2D properties and the 3D bounding box with the 3D properties. However, this assumes that the 2D and 3D centers are always identical, which results in the weakness for 3D detection. The most 3D boxes are biased. To explain this, we need to indicate the difference between 2D and 3D center on the image plane. As we can see here on the right panel, The 3D centers in green are mostly unidentical with the 2D centers in red. The closer the object is to the camera, the more significant is this bias. So how we address this issue? Our approach still detects the object with the 2D centers, but meanwhile, we add additional network heads 3D offset. It regresses the offset delta X and delta Y. So back to the view of the structure, comparing to the center nets. The 3D offsets help us to locate the 3D center, and after that, the other 3D properties will be decoded based on 3D instead of the 2D centers. And we can see the results here. The result of the center net is on the left, while our proposal stays on the right panel. A small modification can already improve the 3D performance significantly, especially for the object on the image boundary, as the arrows indicate. It performs already not bad, but we are still not satisfied. The next key point is joint depth understanding. It can help us to improve further. Normally, we need to pay more attention to the depth estimation since it's tricky, an ear-post problem, and thus plays a crucial role in 3D understanding, especially for monocular detection. And most approaches solve this problem either as classification or as a regression task. However, we should that the combination of classification and regression is more robust than using only a single one of them. To validate that, I will introduce two approaches. First, LID, a classification-dominated approach with sequential linear increasing discretization. And the second, depth joints, a regression-dominated approach with multiple eigens transformation. So LID represents the linear increasing discretization. It was inspired by the approach Dorn, deep ordinary regression network. It formulates the task of depth estimation as an ordinary regression problem by quantizing depth range into discrete bins. Each bin is then classified to one bin. Comparing to uniform discretization, it proposes a SID strategy, which ensures the neighboring bins to increase exponentially, and this can downweight the training losses in the range with a larger depth value. But we still substitute the SID strategy with a normal strategy, LID. LID ensures the length of the neighboring bins increasing linearly. The length of the first bin is delta, then the second would be 2 delta, and so on. Before we introduce the motivation, we can first observe the histogram of the depth in the Kitty dataset. Most objects are gathered between 5 and 18 meters, where we should pay more attention to. We can compare the difference between two strategies from the bird's eye view. For SID, most bins, for example, around 30 of 18 bins are within just 5 meters. However, the distribution of the bins by LID is more evenly and more suitable for object detection. The classification will still dominate the training, but an additional shared layer to regress the quantizing error will help us to refine the classification results instead of solely using the median of the target bin as done in Dorn. Here are the comparison between SID and LID from bird's eye view. Red rectangle here is the ground truth, while the inference is in blue. As we can see here, LID achieves a trade-off between closer and far away objects. In some cases, even LID cannot estimate the depth of the distant object correctly. The error is significantly smaller. Then let's validate how a regression-dominated approach could do. For depth estimation, the baseline center net utilizes the eigens transformation, which converts the feature maps into an exponential range. As shown here, x-axis is the value on the feature map, and y indicates the output depth value. This transformation enriches the depth information for closer objects by putting more feature values into smaller range. As you can see here, the feature map's value between -4 to 5 correspond to a depth up to 55 meters, while feature values for distant objects up to 150 meters accounts for only 10%. As a result, it shows an impressive precision on closer objects but disappointed for distant objects. To this end, depth joint divides and classifies the depth range in two bins, foregrounds or backgrounds, either overlapping or associated, and this can be predefined by the hyperparameter alpha and beta. The depth value will be regressed in both being applying Eigen's transformation respectively. And especially the foreground beams focuses especially on the visual feature on the closer object and regress the absolute depth value D, while the beam of the background captures the character of the farther away objects and regress the residue value of the depth D max minus D. This conversion in background can shift the distribution of the depth value from larger to smaller range. From the blue to orange range on the curve, as you can see, we are supported by more features. Besides, a small trick reference area are applied to support regression tasks. Instead of training and inference on single points, we predefine the area with the scale to see 50% according to width and height. You can define it by itself and utilize all the value within it. When overlapping, the close object will be prioritized. And then training and inference will then happen over all pixels within this area instead of a single point. Basically, this can also apply to all regression tasks. So now let's compare the performance between Eigen's transformation and depth joints. Here, the regression parts of the depth estimation are all supported by the reference areas. Depth joints reserve the advantages of the Eigen's transformation in foreground and improve the performance in background, obviously. So finally, for a quick review, we can see the improvement of all introduced approach above from the statistic more clearly. We performed experiments on kitty datasets. EMH represents an easy, moderate, and hard targets according to the visibility in the image. We firstly only consider the car category and show the average precision in bird's eye view and in 3D space. Also, the RT represents a runtime in milliseconds. As we can see here, bridging the gap between 2D and 3D center can already improve the performance of CenterNet very significantly. Based on this new benchmark, both LID and depth joint can improve the depth understanding and increase the average precision further. And especially a reference area will enhance the robustness for center-based approach and performs the best among our experiments. Comparing to the other state of the art on the same training validation split, Center 3D achieved the comparable performance. Meanwhile, it runs obviously faster and fulfills the requirements of the real-time monocular 3D detection. For example, the best model we have only needed 56 milliseconds for each image in average. We compare further the performance for M3D RPN and Center 3D on official kitty datasets and evaluate with AP40 records and an IOU threshold of 0.7. In comparison with the M3D RPN, Center 3D performs comparable BEV and 3D average precisions. Besides, our approach performs particularly better for hard object detection and cyclist detection. And finally, here are some qualitative results on kitty test sets. In conclusion, our contribution are mainly at first by exploiting the difference between 2D and 3D center, we can estimate depth consistently. And second, our approach uses a combination of classification and regression to understand the hidden depth information more robustly than each method alone. Thank you for your attention and feel free to ask any question.
Thank you, Yunlei. It was a very interesting talk. I have one question. Mm-hmm. So when the 3D volume doesn't fit inside the camera view, or I mean, if the object is partially occluded, or if the boundaries of the object is outside of the view, mm-hmm. then how do you handle it? Maybe even the center of this bounding box of this 3D box is going to be outside of your view.
Yeah, exactly. It's a good question. We can move back a little to the indicator. Firstly, we try to model the object with the 3D center, but actually it turns out to be some problem because sometimes the projected 3D center is outside the image's boundary, which means we cannot address such objects inside of the images. So this is why we also model the object still with this 2D center point. and then add the layer to regress this offset from the 2D center point to 3D center points. In this case, only if the object is some parts visible in the image, we can still use this offset to relocate these 3D centers and decode the 3D properties more suitable.
Okay, I understand. Thank you.
Thank you.
So it looks like we don't have any questions from the audience at this point. In case people don't know how to ask questions, we are using Discord for it. And you can find the link to Discord channel on the website where the program is shown. Feel free to ask questions to the authors directly from there. Thank you. Our next 3 talks are going to be short orals, spotlight presentations. Isabell Hofstetter is our next speaker. Hofstetter.
Hofstetter.
Okay. And her talk has the title Constellation Codebooks for Reliable Vehicle Localization. You can start, Isabell.
Thank you very much. Welcome everybody to my talk on Constellation Codebooks for Reliable Vehicle Localization. As it was said, my name is Isabell Hofstetter and I worked on this paper together with my colleagues at Mercedes-Benz. Vehicle localization is the task of determining the vehicle's pose in the map frame by aligning the current sensor view with the map. And to do so, certain localization features are used that are depicted on this slide by these black dots. Depending on the detected features and the available features in the map, there does not always exist a unique solution for this alignment. And in this case, we have multiple spots in the map that the sensor view could be aligned with. This can be due to indistinguishable features with weak descriptors, or also to repetitive patterns in maps, which make it really hard to guarantee correct and reliable associations. With the zoomed in map section, it should become clear that certain feature patterns are more helpful for localization than others. For example, the ones connected by red lines appear multiple times in periodic orders, whereas the purple or blue pattern only appear once and seem to be uniquely associable. And therefore, in this work, we suggest a new feature association approach that is based on an offline evaluation of all feature patterns that are contained in a map. And the method is demonstrated on a map which covers about 4 kilometers of urban roads and contains about 600 cylindrical localization features. You can see an image on the lower left. The approach involves a full search for the identification of all unique feature patterns in the map. These I will call code words in the following, and they are stored in the so-called Constellation Codebook. At the same time, we also try to exclude all the ambiguous feature patterns that would risk correct positioning. And by the exclusive use of only these unique feature patterns, we can now guarantee correct feature associations, of course, under some assumptions on sensor faults. Let's have a quick look into the Constellation Codebook generation. For the generation of the codebooks, we first divide the map into overlapping map tiles of a size, or in this case, a radius r, and then we extract the unique feature constellations for each tile separately. Herefore, all possible constellations of a fixed cardinality are constructed and compared to each other, which is done by determining the best approximative matching and the resulting residuals. If the mean of the residuals is larger than a predefined threshold, I will call that the uniqueness threshold, epsilon in the following, then the constellation is unique compared to all available constellations and can be added to the Constellation Codebook. In this process, there are 2 constraining factors of importance. First, the tile size R, which limits the search space and should be chosen depending on an initial safe position estimate. And second, the uniqueness threshold epsilon, which represents the minimum allowed dissimilarity between constellations. So it's a measure for the uniqueness and should be chosen according to the localization approach, so the features used and the expected measurement noise. In the following, I will present some results that demonstrate the influence of these 2 parameters. Overall, it can be said that with increasing uniqueness threshold epsilon here in this plot on the x-axis, the total number of available unique constellations in a map decreases, which is also true for increasing tile sizes R, which you can see here in this plot in color. As an example, here is a codebook for the parameters epsilon equals 0.5 meters and R, the tile size infinity. So this relates to the entire map of the 4 kilometers. And for these parameters, we were able to identify about 17,800 unique constellations of cardinality 3 and 4. Each of these constellations is drawn in a different color in the lower plot. Using these codebooks for localization shows the following results. With increasing numbers of available code words, again on the x-axis in this plot, obviously the overall system availability increases. And with increasing uniqueness threshold epsilon, again on the x-axis in the lower plot, so this means a higher dissimilarity between the code words, the percentage of the correct associations increases up to 100%. To sum up, we presented a new approach that provides the means for reliable feature-based vehicle localization. However, the existing trade-off between system availability and reliability became apparent. Depending on the parameter choice for R and epsilon, there are either lots of available constellations on the left, which fulfill a weaker uniqueness requirement, which results in a high availability but lower reliability. Or on the other hand, on the right side, we can identify only few but greatly dissimilar code words that increase reliability while the availability suffers. This brings me to the end of my talk. Thank you for your attention.
Thank you, Isabell, for the really interesting talk. We have a couple of questions from the audience. They are asking how many candidates are there for constellations, because it sounds like there's a lot of possibilities.
That's true. I mean, you can calculate yourself the binomial coefficient. If you have, let's say, in one map section 50 features and you want to compute all candidates of 4 features, so all 4 feature constellation, it's 50 over 4. I don't remember the exact number, but there are a lot. So that's why you should also limit your tile size to extract those and compare those. But it's done offline, so it's not a matter of time for the computation.
I see. And so maybe related to this question, can your model handle or match differently oriented constellations? Let's say if in your measurements you have found different orientations of these constellations, is it able to match them?
Yes, of course. So in this work, I encoded these patterns using a geometric hashing approach, which uses a new coordinate system that doesn't depend on the map frame or the vehicle frame, but introduces a new coordinate system depending on the geometry of the features that can be read in the paper in detail. And so I'm able to match them no matter how they're oriented in the map or vehicle frame.
Okay, thank you. And the final question from the audience. Do you know how your approach relates to FabMap approach of Cummins and Newman? They look at the co-occurrence of visual words to look at unique and less unique combinations. Have you?
I would have to look into that. Okay. Right now, I don't know which work.
Yeah, maybe it's, so the question is on Discord. You can take a look, and if the answer is obvious, you can answer there. But if not, maybe this is an interesting kind of connection with other.
Yeah, definitely. That's an interesting point. Thank you.
Yeah, thank you. Our next speaker is Ujwal Bonde, and he's going to talk about with his work with the title Towards Bounding Box Free Panoptic Segmentation. You can go ahead, Ujwal.
Thanks for the introduction. So I'm presenting this work, which was done jointly with Pablo and Stefan at Slamco Limited. To begin with, what is panoptic segmentation? So most of us would have heard the term instance segmentation, where given an input image, you want to detect all the instances belonging to the countable class or the thing class and assign each of these pixels a unique instance ID. Similarly, in semantic segmentation, given the input image, for each pixel, you want to assign a class ID, whether it belongs to a countable or an uncountable class or the stuff class. Panoptic segmentation is an umbrella term that tries to predict both, that is the class ID as well as the unique instance ID for all the thing instances. As both of these works have been well explored in isolation, the most common strategy is to use a shared encoder followed by split decoders and a mixing module to finally predict the panoptic segmentation. Now, while this approach is valid and has shown good results, we can observe that most of the structured information for panoptic segmentation is already present in the semantic segmentation output. And all we need are the occluding boundaries to predict the individual instances. For this reason, we explore a bounding box free or a proposal free panoptic segmentation method, where we use an off-the-shelf semantic segmentation network and then refine it to predict the final panoptic segmentation. The advantage of doing this is that it allows us to tap into the existing literature of fast semantic segmentation works, as well as explore the trade-off between complexity versus accuracy based on the downstream tasks. So for example, if you want to use this for obstacle avoidance, you would want a fast system, but if you want to use it for 3D mapping, you would want a more accurate system. Our overall architecture is divided into two parts. The first is the backbone semantic segmentation network, and the second is the refinement network. The refinement network itself is divided into three different parts, and I'll be going through each of these individually. Now, given the semantic segmentation output, for each thing pixel, we first predict the instance centers. So this is akin to a half voting map. And using clustering-based approaches, we can then detect the instance centers. Now, it is well-known fact that these clustering approaches are sensitive to the cluster sizes, so it won't be able to handle large changes in object sizes. And for that reason, we only use this to detect the smaller sized instances. On the other hand, for the larger sized instances, we use occluding boundaries, which are detected based on quantized watershed levels. So for example, here the red pixels indicate the first quantized level, which is closest to the occluding boundary, and the gray ones are the ones that are farthest away. Using connected component, we can then detect instances of large sizes. However, the main drawback with this is that if the object is fragmented, we end up getting different instances. And for that reason, we go to the third stage, wherein we do clustering using a triplet loss-based framework, where the candidate pixel is given by the first two stages. Those are the candidate instances that were detected in the first few stages. And the remaining thing pixels are then classified based on these candidate pixels. In this way, we get the clustered fragmented regions, as well as improve the segmentation boundaries. To get a better feel of this, we train the backbone network with each of these heads individually, and then test its performance for different sized objects. If you notice, for the huff head, it does better on the smaller sized objects, and the watershed head does better on the larger sized objects. When we combine all three, we end up getting good performance on all the sized objects. Quantitatively, when we compare our method with the existing panoptic methods, which are proposal free, we observe that we get the best performance both on COCO validation and COCO test using similar size networks or weaker networks as backbone semantic segmentation network. For Cityscape, we get nearly the similar kind of performance. Qualitatively, if you have a look at these are the results. The first row is the performance on Cityscape, and the next two are the performance on COCO. We are able to handle complex scenes with overlapping instances, and still we are able to do quite well. Now, one of the main drawbacks, if you notice, for panoptic for the proposal-based method, for the proposal-free methods compared to the proposal-based methods, is that, including ours, is that the performance does not match up. To understand why this is the case, if you look at the failure cases of our method, we see that when the semantic segmentation network goes wrong, so if it predicts the wrong classes, we don't have a parallel branch to reason out and to correct these detections, which is present in the proposal-based methods. Nevertheless, the advantage of our method is that we can swap the backbone network with cheaper semantic segmentation network, giving better computational performance at the cost of smooth decrease in accuracy. To conclude, we presented a proposal-free panoptic segmentation network which achieves state-of-the-art performance on COCO. Our method is flexible, allowing us to choose between accuracy and speed based on our downstream tasks. Thank you.
Thank you for the interesting talk, Ujwal. I have one question. So how would your model handle adversarial perturbations?
Sorry, what do you mean by adversarial perturbations?
Like, for example, in some small noise is introduced to the image, the classifiers fail often to recognize objects. And have you tried this kind of corner cases or
so we haven't
cases?
No, we haven't tested with such kind of corner cases or special cases. It's an interesting idea. Yeah, I'm sure that it'll help improve the overall performance actually, because if we have tested this on completely different scenarios. So for example, we have tested our method on a completely out of scene, like a train station, and it's done well on those kind of things. But those are generally the bigger networks. So if you want to get it working on the smaller networks, then probably these adversarial trainings might help. But that's just my guess so far. I cannot completely conclude whether it would be the case or not.
Okay, okay. Thank you.
Thank you.
So let's move to the next speaker now. For those of you in the audience who would like to ask questions, please use Discord channel. Our next speaker is Alberto Bailoni, and he's going to talk about his work with the title Proposal-Free Volumetric Instance Segmentation from Latent Single Instance Masks. You can go ahead, Alberto.
Yeah, so you can see my screen.
Yes.
Yeah, perfect. So thank you for the kind introduction. So in our paper, we introduce a proposal-free instance segmentation method, and we specifically focus on the application of neuron segmentation. So why is this interesting, first of all? So in general, neuron segmentation is a challenging task where the input data is given by three-dimensional electron microscopy images of brain tissue. And the task is then to segment each voxel in the volume and assign it to a specific neuron. So as you can see here on the right, the reconstructed neurons can span the whole brain and then are not well approximated by bounding boxes. And moreover, these data sets are very large and then require an efficient segmentation pipeline. So our paper builds on the following basic idea of selecting a patch in the image and then predicting whether each pixel in the patch belongs or not to the same instance of the central pixel. So in this way, the result is a binary segmentation mask of the central instance in the patch. So this idea is clearly not new, but related approaches present several limitations. So some methods, for example, repeatedly predicts these masks across the entire image in a sliding window style. But this is usually very memory consuming, especially on three-dimensional data like the one we consider here. Then we have other methods that start from a seed and then shift the field of view depending on the previously predicted mask. But they are also very computationally expensive and also require like conflict resolution since the instances are predicted one by one after the other. So the model we propose instead also predicts all the masks simultaneously, one per pixel across the entire image. However, all these masks are predicted in a low dimensional latent space. And the reason why this works well is that the combinatorial space of all possible masks is very large. But in practice, if you think about it, the ones that we expect are a very small portion of those. So during training, first we randomly sample some pixels from the output latent space and then apply a small convolutional decoder that outputs the predicted masks. And the model is then trained end-to-end by applying a binary classification loss on the predicted masks. After the training is done, we convert the image into a weighted graph where each node or pixel is connected to a set of neighbors. And we obtain the final segmentation by applying a very simple and efficient graph partitioning algorithm called the mutex watershed. So here, the most interesting question is actually, how do we compute or define the edge weights of this graph? So let's say that we want to compute the edge weight or affinity between these two pixels that I'm showing here in the image. So what we propose is to aggregate information from all the overlapping masks covering these two specific pixels. So for example, the one I'm showing here, or this one and this other one here. And here, for example, we will predict a low affinity since only one of the two pixels is active in the mask. However, we also need to keep in mind that not all the masks are informative. This one here, for example, does not tell us anything about the two pixels because both of them are not active. So in other words, we propose a simple algorithm that relies on fuzzy logic operations and does not then require any threshold parameter from the user point of view, and returns also affinity values with an associated uncertainty. We perform our experiments on the challenging CREMI segmentation benchmark, and we compare our method with the state-of-the-art approach that predicts affinities only for a set of predefined neighboring pixels, like the one you see here on the right. In our validation experiments, we confirm that training single instance masks in latent space improves performances, like you see here in the second column. And moreover, if we aggregate information from the overlapping masks, this turns out to be particularly helpful. So to conclude, we propose a method that achieves very competitive scores on the test set of this benchmark, despite using a very simple and efficient post-processing algorithm. And we think the reason behind this is that by aggregating all this information that is predicted from multiple masks, the post-processing algorithm is able to give a higher priority to the most confident predictions of the model. Thank you for your attention, and now I'm happy to answer questions.
Thank you, Alberto. Very interesting talk. So do I understand correctly that your model is doing segmentation on 3D volumes directly?
Yes, yes. So here for like simplicity, we show it in 2D, but yeah, it's easily generalizable to 3D. So we predict 3D masks yeah.
I see. Okay, that would be my question actually. If you do 2D segmentation and then kind of superimpose them together, and compare this with directly doing 3D segmentation, if you see any difference in accuracy.
So yeah, usually here it's very important on this kind of data set. It's very important to also predict like these affinities in the third direction. So it's important that the model, first of all, sees a 3D context. So it does not see only a 2D part of the data set, but also see like several, like a full cube, because sometimes some of the parts have defects. So it's important to have like context information somehow from the surrounding. And so yes, like having a 3D model like improves a lot. Like it's necessary on this type of data set. So, yeah.
Okay, thank you. And how much computational cost does this introduce?
So like from the training point of view, since we only sample some pixels in the output and we output few masks, like the training as compared to the state-of-the-art method is not so much longer. So I don't know, I would estimate a 25% longer training. Like it's of course a more difficult task, but like that's not introduced too much different. And that inference time, like of course aggregating all these masks requires more time, but it also can be done on GPU. So also I would say like it increases of a 25% the inference time of them.
Mm-hmm.
Yeah.
Okay. So this concludes our session. Actually, thank you. You can stop sharing the screen. I would like to ask all the speakers once more to share their videos. So we are at the end of this session. We will have a discussion session, which is not going to be recorded. So if people from the audience, you have questions, then please connect to the Discord channel and you can talk to the all the authors of all the papers from this session through Discord. And thank you everyone for all of your contributions. We had a very interesting session with many interesting talks. And I hope to see you perhaps next year in person. Bye.
Thank you, bye.